folks, and welcome back to Physics with Captain Rod. The purpose of this video is to help describe for you kind of the basic model of what atoms look like and what their basic building blocks are. So for starters, we're going to talk about three what are called subatomic particles here. All right, and the three particles that make up atoms are called protons, neutrons, and electrons. Right? And I've written some properties over here to the right that are kind of important, or will be important at some point. Right? So the mass of each particle here is written out. So protons have a mass of 1.67 times 10 to the minus 27 kilograms. Right? They're really tiny things. Neutrons have basically the same mass, 1.67 times 10 to the minus 27 kilograms. I say basically because there are small differences if you carry out enough decimals. And the electrons carry a mass of 9.11 times 10 to the minus 31st kilograms. So the electrons are quite a bit smaller. Roughly speaking, I think it comes out to be about 5,000 times smaller than the electrons or than neutrons or protons. All right, now, two of these particles exhibit a very important property. Protons, when are placed next to one another, they exhibit this property that they repel one another. Right? Electrons exhibit this same property. If you take a pair of electrons, get them close to one another, they too repel one another. When you take a proton-electron and get those close to one another, they attract. So the protons and electrons have this repulsive or attractive type of property, depending on whether whether you're a proton-proton, electron-electron, or proton-electron pair. Right? Neutrons don't exhibit this property at all. Right? They don't react in this sort of way. So the property that the protons and the electrons carry that quantifies this attractive or repulsive force is called charge. Charge is measured by the quantity called the Coulomb. And I've written the charge of these three particles over on the right. So the charge of a proton is 1.6 times 10 to the minus 19th coulombs. The charge of a neutron, well, I put none here. Neutrons do not carry a charge because they don't exhibit this force property. And electrons carry a charge that's the same as the proton, 1.6 times 10 to the minus 19th coulombs. I say same, but there's one difference in that in any sort of electromagnetic set of conditions where a proton does one thing, the electrons do exactly the opposite. And that is taken into account with a minus sign on the charge. So the protons and electrons, they have the same charge, but the electron is said to have a, quote, negative charge, unquote, because electrons do the opposite thing as protons do under certain conditions. So we have these three fundamental particles, protons, neutrons, electrons. The masses are written over here, in the middle of the page. Two of them carry this property called charge, the protons and the electrons. Right? And now I'm going to talk a little bit about how they're arranged in an atom. Before I do so, I gotta make myself a new picture, though. Folks, I'm back here, and I've got a picture here of two particles. Now, I put plus signs, and I'm indicating that these are going to represent protons. And there's some sort of distance between these, which I should measure here. And I usually call this distance D or R or something like that. I'll call it D for now. Because these things are positively charged, we know they're going to repel one another, and that force direction is going to be to the right. Well, it will be to the right on the charge on the right, and it'll be to the left on the charge on the left. All right, this force is a special name. It's called the Coulomb force. And some important things about the Coulomb force. Well, one, it depends on these charges. Now, in this example, the charges are these are protons, so there's a charge of 1.6 times 10 to the minus 19th coulombs. In other examples, these could be charged particles that carry more charge than that, but for now, I'm just going to say that this force depends on both of these charges. So I'm going to put, it depends on charge 1, also on charge 2. And it varies inversely with the distance between them. And what that means in physics, inverse variation means basically when the distance gets bigger, the force gets smaller. So mathematically, the distance goes on the bottom. And it turns out that the distance is being squared. So this law, and I'll write it out in a more detailed sense in another video, but this law is known as Coulomb's law, that the force between two charged particles depends on the product of the two charges, and it varies with the square of the distance between them. It varies inversely with the square of the distance between them. So basically what that means, if I were to take this charge and double it, then the force would double. If I were to take this charge, double that, the Coulomb force would double. However, if I were to take the distance and double that, well, for starters, because the distance is in the bottom of the equation, the force gets smaller, not larger. And because it's being squared, the force actually would change by a factor of 4. So I'm only going through this to talk about the qualitative or conceptual relationship between the force, charge, and distance. The important thing to get out of this discussion is that the force depends on the charge, both charges, right? More charge, more force. The force varies inversely with the distance. So as the distance between particles gets bigger, the force gets considerably smaller. And keep this in mind. I'm going to pull up another picture here and talk a little bit about the structure of an atom now. Folks, I'm back, and I've got a picture here I want to talk about. So in atomic structure, the protons and neutrons, they live in a central region called the nucleus. So in this picture here, this kind of group of particles is my kind of picture representation of a nucleus. I kind of color-coded it. The red particles are representing positively charged particles. In this case, they would be the protons. These gray particles would represent the neutrons. And then the electrons are outside the nucleus, going round and round in these regions of space that are called shells. Now, one thing I need to talk about in this picture, this picture is by a long shot not to scale. If the nucleus of an atom were actually like this size, the first orbital shell here, this distance here, would be many millions of times larger than I have it drawn. It would not be in the building I'm in. It may not even be in this town, right? The orbital sizes are very, very large compared to the nucleus. Same thing with these electrons. If the nucleus were the size that I have it drawn, you would not be able to see the electrons that I've drawn here in this first shell that I've kind of color-coded in green. They'd be many, many, many thousands of times smaller. But in order for you to see them and for us to talk about them, I had to kind of blow them up. So keep that in mind, that the scale, almost any model of an atom that you see drawn is not to scale. So again, we got the central location here called the nucleus. That's where the protons and neutrons live. Then we have this region called shells, and this is kind of a semi-side view here. You got to imagine these electrons going round and round. If we did kind of a top view of this, these circles would be round. And again, these regions where the electrons are, they're referred to as shells. And the way I would describe it is this. Imagine this electron just going round and round and round. And imagine that as it goes around, it could leave a little trail of paint in space. Much like a person painting. Oops, gotta answer my phone. Back. Sorry about that. So again, getting back to what's happening here. So imagine these electrons going round and round and round and dragging paint with them. Much like a truck as it drives down the road painting lines. And what would happen is eventually these electrons would map out this three-dimensional surface. And that surface is representing where the electrons are spending their time. And those regions, those are what are called the shells, those regions in space there. Now, also notice I drew 2 electrons in the first shell and then 1 electron in this outer shell. And I'm going to get into the details of that later. For now, I want to get back to just the basic principles here. The atom that I've drawn is a lithium atom. And lithium is an atom that has 3 protons in its nucleus. And the number of protons in the nucleus of an atom is what defines an atom. It's what makes an atom an atom. This atom is lithium because it has 3 protons in its nucleus. If it didn't have 3, if it had 2, it wouldn't be lithium, it would be helium. And if it only had 1 proton in its nucleus, it would be called hydrogen. So the number of protons in a nucleus, number of protons, this is what defines an atom, and this is called atomic number. Now, you'll also notice in this picture that there are 3 of these gray particles I put in the nucleus. Those are representing neutrons. And you'll notice I've got 3 neutrons, 3 protons. Well, kind of on average, usually, if you have 3 protons, you'll usually have 3 neutrons, but you don't have to. See, remember, the neutrons are electrically neutral, so they're not really repelled by the protons. These particles are held together by what's called the nuclear force, and it's reasonably easy for another neutron to get in here and maybe get stuck to this nucleus. So, in the example that I have here, I had a 3-proton, 3-neutron nucleus. But it's possible, if you look at a sample of lithium, you're going to find that some of the atoms maybe have 3 protons and 4 neutrons. And, atoms with different number of neutrons are called isotopes. And again, I'll talk a little bit about that in another video. But for now, generally speaking, the number of protons, number of neutrons is right around the same number. Now, you also notice I drew 3 electrons. So in general, if you have 3 protons, you should have 3 electrons as well. Now, if I drew an atom with 4 protons, it would have 4 neutrons, plus or minus maybe a little bit for isotopes, and it would have 4 electrons. If I pick the 10th atom, number 10 on the list, it would have 10 protons, 10 neutrons, maybe some more for the isotopes, and 10 electrons. Now, it turns out that the electrons don't have to be necessarily bound tightly to the atom. This electron out here, right here, it's kept attached to the nucleus via the Coulomb force that I talked about earlier in the video. But if we look at the Coulomb force between all of these particles, let's talk about this electron and the nucleus. The Coulomb force, right, would be inward. As far as this electron is concerned, it sees 3 charges here in the nucleus, and it's attracted to all 3, and it's relatively close. So for that reason, the Coulomb force is a very, very strong force as far as this particle is concerned. For this electron out here, the Coulomb force is much weaker, because as far as this electron is concerned, there are 2 things working against it. One, all of this charge is in relatively the same place. There's 3 positive charges and 2 negative charges. So as far as this electron is concerned, there's really only an effective charge of about +1 or positive 1.6 times 10 to the minus 19th coulombs in this region. And second, this electron's quite a ways away. So remember, the Coulomb force falls off with distance. So because this electron sees much less charge than this guy does, and he's quite a bit further away, the Coulomb force keeping him attached to this atom is very, very weak. So long story short, it's very easy for this atom to lose this electron, just have it gone. In which case the atom would now be positively charged, and it would have a positive charge of 1.6 times 10 to the minus 19th coulombs. So just kind of to summarize this, atoms are made up of 3 types of particles: protons, neutrons, electrons. The protons and electrons carry this property called charge, meaning that they repel or attract depending on the combination. Neutrons are electrically neutral. As far as the atom is concerned, the neutrons and protons, they're in the central region here called the nucleus, and the electrons live in these regions called shells, right? An atom will have an atomic number. That's the number of protons it has in its nucleus, and that's what makes an atom an atom. That number doesn't vary. In this case, the atomic number is 3. If it were and the atom is lithium, if it's any other atomic number, it's a different atom. The number of neutrons is usually right around the number of protons, but it can vary some, and that's what isotopes are. Atoms with they're the same atomic number, but they have different numbers of neutrons, right? Then the electrons, they live in these regions called shells. The shells, again, they're just regions in space where the electrons hang out. Typically, whatever the atomic number is, that's how many of electrons the atom, I'll say, may start to have. However, some atoms can lose an electron or maybe 2 pretty easily, or some atoms can gain 1 or 2 electrons pretty easily, in which case you haven't changed the atom. Like if this atom loses this electron, it's still lithium. It's just that, the atom carries a charge then. So that's probably enough for this video. I hope this is, does at least some sort of justice here describing atomic structure. And hope you have a great day.